Hi everyone, my name is Thomas Bailey from Riverside Research, and I want to take some time today to talk about how we're taking DARPA SafeDocs secure parsing technologies and transitioning them over to the open architecture community through SOSA. We're going to show a demonstration of a SOSA-aligned sensor system running on top of a drone and how it communicates with the simulated military ground station. The communication line in between these two is going to be secured via our secure parser, which was developed using SafeDocs technologies and ensures that all information is well formed and conformant to the specification of the protocol.
Our demonstration begins with this harmless little drone. This homemade drone has a camera module that can be controlled from our simulated ground station. We can use this directional keypad to turn the camera up, down, left, and right. These commands are communicated over RF to our drone via a DoD open architecture protocol that we'll talk a bit more about later. This works great for sending command messages to our mission system, but like any communication, this line is subject to compromise. This means that an adversary could come along with something like this Flipper Zero, read that over the air traffic, and wreak havoc on our system. This could lead to failure of the mission, loss of military resources, or even worse, harm to the warfighter. We're here today to show you how we can protect these operational platforms by transitioning secure parsing technology developed under previous DARPA contracts.
Before we dive into the demo itself, I want to take some time to step you through what the system looks like and what the demo is actually going to show. Our sensor system consists of a drone with a homemade camera on it that uses Raspberry Pis to simulate an aviation sensor system. This is running our secure parser, which we can turn off and on through a switch. And what the secure parser aims to do is only allow formatted, well-trusted data to pass on to the actual sensor system and operate the camera, while untrusted data that it receives over its RF receiver is dropped at the edge. The data that it receives should be coming from the simulated ground station that we'll talk about later, but you'll also see that we've set up an adversarial man in the middle to show that we can inject malicious packets into this sensor system that our secure parser is able to drop. On the other end, we have our ground station, another Raspberry Pi with a simple up, down, left, right keyboard attached to it that aims to transmit via RF and move the camera up, down, left, and right. And it's doing so via SOSA-aligned open architecture standards. We're using MORA, the Modular Open Radio Frequency Architecture developed by Army CFI-ISR, and the messages that it uses to communicate between our ground station and the aviation sensor system. And the goal here is that these two systems, the ground station and the sensor system, could be talking completely different languages, but as long as they communicate via the same open architecture standard, we can secure that communication line and ensure that the commands being sent from the ground station are successfully received and communicated to the drone. Now, the life of a good packet is fairly simple. Our controller inputs a command which is sent via the Raspberry Pi and turned into a MORA data message, which is what you see in the bottom there. Then we use our RF transmitter and send that MORA data message as RF packets, which will be received by our aviation sensor system. On the other end, we have our RF receiver that's running on our drone. That receives the RF packets and breaks them down into their raw binary. Now, with our secure parser on, the secure parser will check to make sure that the information it's receiving is exactly conformant to the grammar derived from the specification of the protocol. In doing so, it can ensure that only formatted and trusted data is accepted by the sensor system and sent to the rest of the system. Thus, we know that the input that actually reaches our drone sensor system are valid commands and are able to move the camera.
Now let's see that in action as we follow the life of a good packet with our drone. Things are easy enough here. We can simply press a key on our control pad, then the ground station will transmit a message over RF with the command for our drone. The drone receives that message and executes as much of those instructions as it can. In this case, a simple command from the ground station causes the drone camera to turn left to set a mount. As this is running, take a second to look at the parser box on the side of the drone. You'll see it's divided in half, and the truth passed and device passed lights light up. This indicates that the packet that was received should have been accepted by the system and was successfully passed on to the system.
But the life of a bad packet looks a little different. We used the Flipper Zero, and if that doesn't scare you, it probably should. Flipper Zeros are commodity hardware that can be used for a variety of nefarious purposes, but also for valid hacking purposes. We used our Flipper Zero to sniff RF packets and use those readable binaries from an attacker's perspective to craft malicious binaries a priori that we uploaded to our Flipper Zero. Thus, our Flipper Zero can act as a man in the middle for this communication, attempting to hijack the communication and act as the ground station and broadcast these malicious RF packets over to our sensor system. This is very akin to something you could see in a real operational scenario, as flippers are commodity hardware that with extensions and the correct antenna can be used to broadcast these types of messages to low-flying aviation systems. But the system looks a little bit different when we turn our parser off. We still receive everything the exact same and break it down into its raw binary, but with no secure parser on, the normal parser of a system would attempt to reconstruct as much as it can to pass on to the sensor computer in the hopes that it can attain some type of command. And this is very similar to what we see in the wild today. Systems without secure parsers are very liberal in what they accept and attempt to make some sort of command out of what they see and drop or reform parts of the packet that aren't conformant to what it would expect. Thus, our sensor system receives a malicious packet which can do a variety of things such as cause bad output commands for the camera or increase slowdowns and cause denial of service attacks.
Let's continue by looking at how that bad packet would traverse the airwaves to our drone. The adversary can pick up something like this Flipper Zero online for a couple $100 and suddenly have a slew of malicious hacking capabilities at their fingertips. Luckily, we'll be using our powers for good today, starting by sniffing ground station messages that are in transit to the drone. We intercepted these known good messages and crafted malicious packets a priori, packets that will cause unintended behavior to the camera. Thus, we can show how easily sending that crafted packet causes the camera to jitter, move around, and potentially lose mission-critical data. Let's look at that one more time, but this time focus on our parser box once again. When we send this malicious packet, you see that the truth rejected light comes on as well as the device passed light. This means that the message should have been rejected, but was incorrectly accepted by the device.
Now the RF receiver receives those malicious RF packets, but if we have our secure parser on, you can see that we still break that down into its raw binary, but we notice that there are parts of it that are malicious that weren't there before. Our secure parser on, though, rejects these packets because it notices that the syntax and the format of that message doesn't exactly conform to the Morse specification that the Army and Air Force systems are agreed upon to use.
It's a different story once we turn our parser on. Just as before, we're sending the same malicious packet via our Flipper Zero to the drone. The only difference this time is that, as you can see, nothing happens. Let's see that again, but this time, focus on our parser box once again. Unlike before, when we send our malicious message with the parser on, we get two similar lights, device rejected and truth rejected. This indicates that the parser should have denied the malicious message and that it did indeed prevent the malicious message from ever having the chance to do harm to our sensor system on the drone.
Now, before I show the actual demonstration, I just want to show the full system diagram so I can break down exactly what's happening. So as we talked about earlier, we've got our UAV sensor system that has our camera on it, and we've got the attacker using a Flipper Zero attempting to man in the middle of the connection. Similarly, we've got a ground system that accepts inputs and sends those via RF to our UAV sensor system on that open architecture communication protocol. Now let's dive into the demonstration itself. You'll see here that as we talked about earlier, we have our drone, our Flipper Zero, and our command station on the right. These are communicating via RF with our parser box on the left. The parser box on the left of the drone has two different sides. The left side of the parser box says whether the packet that it receives should have been passed to the system or should have been correctly rejected. And on the right side of the parser box, it shows what actually happened, whether the device received the packet or whether the packet was rejected and dropped. And we're able to turn our parser on and off via that switch on the box. On the right side here, we have our command station, which is communicating with the drone. We're able to input commands up, down, left, and right to move the camera accordingly. And you can see that as we do so, the parser box on the left lights up, showing us that yes, we should have passed this packet onto the sensor system to move the camera, and we did successfully pass it on to move the camera. And what this means is that we're using the default parser that comes with Mora because our parser is not turned on the parser box. But even with it turned on, we can show that these types of messages, these known good messages that are coming from a valid source, should be well formed and compliant to the specification of the protocol and should actively be passed on to the sensor system to affect the drone. Now we can use our Flipper 0 and the adversarial message that we crafted a priori and send that over to our sensor system. Now it goes by pretty quick, so hopefully you didn't miss it, but obviously the camera has very erratic movements when we send it this malicious package, but also look at the parser box on the left. It's saying we should have rejected the packet, but we're not. It's being passed on to the sensor system, and that's what's causing this erratic movement that you're seeing. Finally, let's look at what happens when we turn our parser on via the switch on the parser box. We're able to send that same malicious package, and it's a little boring to watch, but what you're seeing there on the left of the parser box is saying that we should have rejected the packet, and we are successfully rejecting and dropping that packet, meaning it doesn't corrupt our sensor system as it did before. But when we send valid commands via our simulated ground station, we can still move the device as if we were doing so before without the parser running. And this just shows that our operational technology is restored without adversarial influence via injection attacks. But why does this really matter? Well, it matters because this style of adversarial injection attack is not uncommon and has the ability to wreak havoc both on the warfighter and the devices that they use. Many memory safety bugs that we see today can be classified as parsing bugs, and secure communications typically only use encryption for hardening of the communication line between devices. Rather, SafeDocs posit that hardening of the boundaries of these devices is necessary for truly secure systems. Secure parsers such as the ones that you saw here today enable this interoperability between systems for these advanced tri-service missions and ensure that the information being received by one system is well formed and is conformant to the specification of the protocol that the two systems are operating over. Further, these secure parsers have the ability to enhance open architecture security in a variety of ways. Interoperable data formats are necessary for communication across the services and between government and industry platforms. And secure parsing enables this secure data protocol design by default, because as we learn lessons from what a good data protocol looks like and what we can build parsers for now, we know how to design more secure data protocols in the future. And we're able to prove conformance and more rapidly integrate these types of systems together when we know that they're speaking the same languages. If we know that my device is using a secure parser and it's able to receive communications from another device, then we know that the other device is sending things in a way that is exactly conformant to the specification, and we can make a conformance use case for that as a result. So I encourage you to look more into this open source tooling and to see the benefits that secure parsing can provide, not only for the open architecture community, but across a wide variety of operational platforms, both in the DoD and throughout industry. Thank you.